or not doing much. So in addition to this black hole mass, like I mentioned, this other quantity is the how fast they're growing, and this is usually parameterized with the Eddington ratio. So Eddington is the maximum limit of accretion. So why is there a maximum that we calculate? So a black hole is very massive, right? So gravity will attract the gas. So gas would fall in through gravity. So they would increase the accretion. But once the gas is being accreted, it forms an accretion disk, and that accretion disk is quite luminous. So that makes radiation pressure. So radiation pressure will want to push the gas away, preventing it from accreting. So we have basically a competition between gravity and radiation pressure. So if we assume a spherical geometry, so a sphere, that limit is it's called the Eddington limit, basically. So the limit of Eddington in the log scale here is 0. So you can see that you have a very wide range. So this is like 6 to 7 orders of magnitude of accretion rate. So very, very low accretion rate. For example, the Milky Way does not even really qualify as an HGN because the accretion rate is so low that in a different galaxy, we would detect it. And then the quasars are the other extreme. So they're massive black holes and they're very luminous. And high, which means they have also a high Eddington ratio. All right, so how do we learn about these different AGN and how do we measure black hole masses, for example? So one of the best ways to do this is spectroscopy. So this is why now what I want to talk to you is how are we gonna try to answer some of these key questions about black holes and AGN by using a very large spectroscopic survey, and namely I'll be introducing the DESI survey. Okay, so key questions. I said we understand some things, but we don't understand other things, right, about AGN and black holes. So how did they form originally? So how did supermassive black holes form? So we have some scenarios and hypotheses. So we start from black hole seeds, but how the seeds form, how massive are those seeds? So basically the black hole seeds would be like the first black holes. And then as the universe evolves, when and how often are the black holes growing? So do they grow in one big phase, like one big episode, and then they stop? Or do they grow almost constantly, just at low level? Or they have up and down and up and down? So how does that work? And what needs to happen? So we call this usually AGN triggering. So basically, if you have a black hole, what would trigger the activity, what would make it have the accretion disk? Is this related to the galaxy? Does the galaxy have to experience something to send this gas toward the black hole in the center? And then how often they're basically on or off. So sometimes this is called a duty cycle if you're reading the literature. And then a big question, which unfortunately I won't have time to get into too much today, but maybe we can follow up some other time. How do the black holes impact their host galaxies? So we know that when they have an accretion disk, I mentioned already this radiation pressure, but in fact, there can be so much radiation that this can heat up and push the gas from the host galaxy. So if we remove gas, it means that galaxies don't have enough material to form more stars. So galaxies are becoming quenched. So the star formation can either drop or be completely stopped. So sometimes we say that this kills galaxies in a sense, but at least it stops the star formation. So in order to answer these questions, and then I will spend some time during this talk about this, but we need to find the black holes, but mostly we need to find them in our active phase, so we need to find the AGN. So this is AGN identification, and I'll talk about this. All right, so spectroscopy. There are many spectroscopic surveys. Today, I want to focus on the Dark Energy Spectroscopic Instrument survey. This is still ongoing, and it's very new in the sense that it started observing on the sky in 2021. And it's a 5-year survey, so it will go until 2026. And this is installed, the instrument is installed on a 4-meter Mayo telescope in Kitt Peak, Arizona. So it's actually not too far from here. Sorry about my cat. She likes to join all my Zoom calls. And right now we already have, so the first phase was survey validation. So I'm linking here, putting the references for the survey validation paper. I guess the one word conclusion, or maybe two words conclusion of survey validation is that it works. So we managed to accomplish what are the requirements. So we think we will successfully complete the survey and measure dark energy. And then we had an early data release, or EDR. So you can see the paper here. And I have a slide to show you also how to access the data. So the early data release is based on just the survey validation data. So it gives you a bit of a clue of what's going on, but you see this is already many data. So the picture here shows the Mayo Telescope dome, so in Kitt Peak, Arizona. And then this is an artist illustration. We do not cut the dome to show basically the shape of the telescope. And then there's a room with the spectrographs. So because DESI is a very ambitious project, we want to obtain spectra for about 40 million galaxies and quasars. And this is because to measure dark energy, we want to make the largest 3D map of the universe ever made. And then I think another mission that will obtain even more spectra is Euclid, and they will obtain spectra as a different range of redshift. But together, DESI and Euclid are very much unprecedented, like much larger than all previous surveys before. And then to give you a sense of scale, so this is actually me here with my red jacket, and this is inside the dome at Kitt Peak. So this is a 4-meter telescope, and then what is needed to make to obtain so many spectra over just 5 years to get 40 million is we had to have a very highly multiplexed instrument. So at the top in this black tube here, so the light hits the primary mirror and is a giant glass corrector. And then we take 5,000 spectra at a time. So this shows the footprint of DESI. So one footprint with a 5,000, we have 5,000 robots that each will place the optical fiber on one target each. So either a galaxy or a quasar or sometimes a star. And then, so they arrange in a circle shape. And then this shows the background. This is the Andromeda galaxy on the sky, which is several times the size of the full moon. So this is, it's a 8 square degrees field of view. And then this was one of the kind of press release images from a while ago, but basically one spectrum from one fiber here happens to be a quasar. So this is obviously in the background like way far compared to Andromeda. And I would like to show this animation to get a better sense. So some of you may be familiar with the Sloan Digital Sky Survey, or SDSS, which was the predecessor, and also at the time that was the new kind of largest spectroscopic survey. But for SDSS, each pointing was a metal plate with holes, and people would place manually fibers in each hole of each plate. So that was a lot of manual work. And with DESI, instead it's 5,000, we call them fiber positioner robots. And this video will show how they move. This should only last 20 seconds. So basically we're kind of zooming in, and then each one needs to precisely align the fiber. So they have 2 axes of rotation, so which allows them to position each fiber individually. And also the robots have to be pretty close together. So they have to, the software is quite advanced because we have to make sure there's no collision while they all get positioned. This only takes a few seconds to get all 5,000 positioned, less than 1 minute. Okay, so thanks to these revolutionary breakthrough, this is how we will ultimately achieve 40 million spectra. So the DESI survey is divided into different kinds of targets. So there's a Milky Way survey for about 10 million stars. And then the Bright Galaxy survey, which mostly is for brighter galaxies, so we can observe them in also brighter time. So those are lower redshift, and we'll have about 10 million. And then the other tracers, there's a luminous red galaxies, or LRGs, and then emission line galaxies, or ELGs. So emission line galaxies mostly rely on finding the O2 doublet in the spectrum, and we can observe that out to redshift 1.6 or so. And then quasars, I already mentioned, we call them also QSOs, and those we can see to the largest distances, so the furthest away. And then we're going to get over 2.5 million, probably even closer to 3 million quasars. So those we can see at least up to redshift 3.5, and I'll show some examples of even higher redshift quasars. And then I mentioned briefly that we have so far the early data release is available since last summer, June 2023. And this has only 1.4 million spectra for galaxies and quasars and over 450,000 stars. And this figure here shows the redshift distribution per target class. So the bright galaxies at low redshift, less than 0.5, and then the luminous red galaxies are mostly between redshift 0.5 and 1. And then the emission line galaxies mostly out to redshift 1.6, and quasars all the way to 3.5 and a bit more. So this figure is truncated here, but there's a bit of a tail. So you can see we probe quite a big range of redshift here. And then this is also from the early data, and I like to show it because the main purpose of DESI, again, is to probe dark energy, which requires knowing precisely the 3D structure of the universe and the large-scale structures. And this animation shows scanning through a slice. So a slice is in 2D, and then it's scanning in the third dimension. And then the different colors are the different kind of tracers, whether they're quasars or ELGs or LRGs and so on. So you can already see by eye, basically, and this is, again, just the survey validation. So just a small slice and some pointings that we already see quite nicely, and a lot of structure. So I want to show you, so I'm not allowed to show you all the latest data, but I can show you at least the progress that we've been making. So this is a number of spectra that we've been obtaining with the dates. So there's some gray bands here when the telescope was closed for different reasons. But when it's open, you can see there's a very fast and steady progress. And as of March 20, we had over 30 million spectra already for galaxies and quasars, and then almost 11 million spectra of stars, which gives us radial velocities for stars. So already a while ago, maybe even already 1 or 2 years ago, we had already enough to make the largest 3D map of the universe. So we just keep making a bigger map and a more complete map. And then I can make this available after, but there are different ways you can already yourself use the early data release. So this is the DESI official website that has all the files, but I'm also involved in both the Astro Data Lab and Sparkle. And Astro Data Lab is a science platform, so the software installed, the data is already all there, and you can create a free account if you're a researcher or a student. So datalab.noirlab.edu. And this as a searchable database, so you can search the catalogs for DESI data. And Sparkle is a spectral database, so the spectra, the DESI spectra in 1D, are in the database. And then you can also query them and retrieve them, for example, we often use Jupyter notebooks, so we have Ubiquitous that you can use with both of these tools here. So I encourage you to take a look, and I can share my slide after. All right, so now let's say, what can we learn using the DESI data about black holes and AGN, which is what I want to focus on for the rest of the talk. And so this is also a map made with the early data. And then as a reminder, each dot here is a galaxy or a quasar. So they all have a spectrum. So what does that look like? So I want to show you here just a variety of spectra. So this is not just AGN and quasars, this is everything. So I'll just show you an example of each kind. So emission line galaxies, right? They're very faint. So in the image, you don't see much, but there is something there, I promise you. There's very little continuum. So this is just some small region of the spectrum. So this is a wavelength in angstrom here. And then you can see the O2 doublet, which is the main tracer we use for emission line galaxies to measure the redshift. So quite well resolved with DESI. A quasar, this is a distant quasar that has what we call the Lyman alpha forest. So this is a broad Lyman alpha line in the spectrum. And then all these absorption lines here on the left at shorter wavelengths, each one is a Lyman alpha absorption, and together that makes the Lyman alpha forest. And then this is, in the image, it looks like just one star here, but this is in fact a binary. So there's a white dwarf and an M star together. So that combines together to make the spectrum. And then this is one example of a bright galaxy. So in this case, the spectrum is nice because we have a lot of continuum, which tells us information about the stars in that galaxies, about the stellar populations. And we have, in addition, emission lines. So these emission lines can tell us about the ionized gas in this galaxy. Luminous red galaxies, by definition, normally they're not, they don't, because they're reddened because they don't have a lot of new stars. So in this case, we mostly see just the absorption lines and the breaks in the stellar population spectrum. So this is a stellar continuum here that we see. And then this example here is a reddened quasar. So these are a bit more rare as far as quasars go. So it's a red dot in the image instead of a usual blue quasar. And then this has a broad line, like you said, this is showing a magnesium 2 UV line. And then, but otherwise, the spectrum is very reddened. So if I, and I'll show you, and I have other slides to show you basically blue versus red quasars. So you'll see more directly what that means. Okay, so now what can we learn and what can we tackle with having all these spectra? So let's revisit the questions I posed before. The first one is, how did supermassive black holes form? And then, so basically, what can we learn about the black hole seeds? There are two main approaches to learn about black hole seeds. One of them is to actually search for the highest redshift, most distant quasars. So why do we want to do this? Well, let's say the universe is quite young. So if we go to redshift up to 5 or 6 or even 7 or more with JWST, so the universe is quite young. So if we find a black hole, we know that it had to grow, it had to grow fast to reach the mass that it has at that redshift. So if there's already, let's say, a black hole that's several million times the mass of the sun, so either it needed a very large seed, or if it had a small seed, that seed had to grow really fast with a very high, we would even say super Eddington accretion. So basically, one way to put constraint on the seeds, so how many seeds, how massive are they, how fast do they need to grow, we want to search for the highest, most distant quasars. So DESI so far, so it's not breaking records, we don't have the highest redshift, but it's a very large survey. So I didn't mention this, but we cover 1/3 of the sky, so 1/3 of the sky. And then there is a special program that specifically with target selection is looking for a candidate of these higher redshift quasars. And importantly, they're trying to find, in this program, we're trying to find quasars above redshift 5. And with just the early data, there were already 400 new quasars in the redshift range between 4.7 and 6.6. So if you remember, most of these quasars go to redshift 3.5. So this is really pushing to higher redshift. And of these 400 that were found, 220 were new at redshift greater than 5. So they were not known previously. Some of them, they were already known from SDSS or other surveys. So this first paper here, well, this shows an example of the spectrum of such a high redshift quasar. This one is at 5.8. And then this is a Lyman alpha line of the spectrum. And anything, this is here in nanometer instead of angstrom, but everything basically is absorbed. So this such a high redshift, there's so much intervening gas that the Lyman alpha forest basically absorbs everything. So there's not much light left at all. So it's a very distinct, clear sign of that the spectrum corresponds to a high redshift quasar. So this is again getting started, but it's very promising that we'll have, this is only a third of that program, so we'll have many more to make such studies. And then the second approach, instead of looking for the highest redshift quasars, we could say, well, some of those early seeds, they will survive perhaps in dwarf galaxies. So let's say a seed formed in a small galaxy that did not have much more, many more mergers. So perhaps the seed will be a leftover right now. And this would look like an intermediate mass black hole. So it would not be supermassive. And I have, I think, a figure right here. So intermediate mass black holes would be somewhere between supermassive black holes that are usually thought to be over 1 million times the mass of the sun, and stellar mass black hole, which are maybe up to a few hundred times the mass of the sun. So this whole intermediate range here, we're looking for, okay, those are harder to find. There are very few known even so far, but this is a place that we're an active field of study. And then this is work led by postdoc Raga Pucha, who's now in Utah, but she started this as a grad student at Arizona here. So with DESI, the idea is to search for active black holes in low mass galaxies, and then for some of them that also have a broad line measure the black hole mass. So already with the early data, DESI is finding many more AGN in these low mass dwarf galaxies that perhaps some of them could have intermediate mass black holes. So this figure shows the mass of the host galaxy, so not the black hole mass, but the mass of the galaxy versus redshift. And then DESI is in black, and those are the histograms, so the distributions of the redshift distribution and the mass distribution compared to previous surveys, and namely compared to SDSS and gamma in orange and blue. And you can see already that we're finding so many more objects, just thanks to the DESI having a large area, but also we have fainter targets, so fainter galaxies, and we have higher spectral resolution. So this everything is helping basically, and we think we might even find over 10,000 AGN in dwarf galaxies at the end of the survey, which would really be a record breaking compared to everything done so far. Okay. So the next big question is when and how do black holes grow, and are there and we think there are more than one ways, like more than one triggering mechanism. And I'm not going into details here, but there's a whole slew of literature about this. So basically, for example, the papers would cover do we need just an internal mechanism, like some way to bring some gas around the black hole, or do we need an external mechanism, like a merger of two galaxies or more? And then in the case of a merger, this could represent a special phase of galaxy evolution. So I want to touch on this because we have one project specifically looking for red quasars. And I already showed before an example of a regular quasar versus a red quasar. But what's interesting about red quasars is possibly, there's also, again, a body of work on this. So this is not just the only work, but if we have a merger of two galaxies that are gas rich, all the gas and dust might form a cocoon, which will really obscure the central source, in this case, the central AGN. So what we have in this case is basically a lot of dust in front of the AGN in the accretion disk, which will redden the entire spectrum. So we might expect in this scenario that first we have a red quasars in this very enshrouded phase, and as the quasar itself is making all these winds and is blowing up gas, it will become uncovered and then become a regular blue quasars, possibly with some radio jets. And then eventually the AGN might, or the black hole might stop accreting, so it would be just a regular galaxy. So because, again, thanks to the statistics and having this large survey with DESI, this is work led by Vicky Fawcett, who's now doing a postdoc in Newcastle. And she found that with DESI, we can find even redder quasars compared to what we could possibly do before with SDSS, at least on average. So this is excluding, I guess, ultra-red quasars that are selected in the near-infrared. But as far as optical selection goes, this figure shows stacked spectra, so average spectra. And then the blue line is a regular blue quasar here, and also the least, or basically they're consistent with no dust or no reddening in the DESI survey. And then SDSS is a dashed blue line, which is underneath. And then all the other color lines have increasing reddening, so meaning more dust. And in fact, the yellow line, it's maybe hard to see, but it's close to that dotted line at the bottom here. So this maximum reddening corresponds to about 4 magnitude of reddening in the optical. So very highly reddened and consistent with applying a dust model to the blue spectrum, which is what the dotted line is. The dotted line is applying a dust model to a blue spectrum, so you can see, okay, this looks like a foreground screen of dust. So far, there are indications that these red quasars are indeed corresponding to a special phase, because in addition to having more dust, they also have more radio jets, and they also have different properties of the radio jet. So we think there's something fundamentally different, and it's not just dust because of an orientation effect, which I'll talk about later too. Okay, and then about how often do they switch on and off? So, and I mentioned before that this is a bit of a duty cycle, but we can actually find this switching on or off can take place on a scale of a few years, so human years, lucky for us. So we have one paper so far, and we have other papers in preparation, searching specifically for what we call changing look AGN. So this is comparing the spectra, for example, from SDSS, and then, which was a few years ago, compared to DESI. So we have that few years difference, and see, are the spectra the same? Is the quasar or the AGN switching on, switching off? Can we find any differences like that? So this figure here, the top panel shows the magnitude versus the year. So this is MGD date. And then the SDSS spectrum was obtained when the object was quite bright, and that same object, or quasars, become fainter when we took the DESI spectrum here. So the different colors are different bands, but you can see there's like some fluctuation. There's like a dip where it becomes fainter, and this is what, by chance, this is when we obtain the DESI spectrum. So the SDSS spectrum in blue is brighter, and it's also bluer, so in a short wavelength, compared to the DESI spectrum in red. And there are still some broad lines in even the DESI spectrum here, but clearly in SDSS we would say this is clearly a quasar, whereas the red spectrum we would say, okay, this has an AGN because it has a broad line, but it doesn't look like quasar luminosity. And the difference shows a big switch off in this case. So this is only one example. This paper is finding the order of like hundreds, again with early data, and we have many more coming. So this is, again, just a teaser to give you an idea, but we think that the most likely explanation is that this black hole and others, the accretion disk itself is changing. So maybe it stopped accreting for some reason, and maybe it starts again, or this is something that reduced or quenched the accretion disk itself. All right, and then the last part is about finding AGN and supermassive black holes that are in their active phase, so AGN and quasars. So I've already mentioned some of this before, in the sense of what do we see in the spectrum, and how do we know in a spectrum that there's an AGN, and also what can we measure. So this cartoon here is one of versions of the AGN unified model. So according to the model, there's a supermassive black hole in the center surrounded by the accretion disk. And this you've seen in the ARCGIS illustration before. We think it's a very bright accretion disk of swirling hot material. But this accretion disk is emitting lots of radiation. So this is ionizing gas. It's ionizing clouds of gas that are the BLR, the broad line region. So these clouds of gas are very close to the accretion disk. They're rotating fast because they're close to the black hole potential well, the gravity, so they have to rotate fast. So these, because of the fast rotation, makes very broad lines in the spectra. And then we have these other gas clouds called the narrow line region, or NLR, and those can extend very far out, and the accretion disk shines on these clouds, so they get ionized, but they're not moving so fast around the black hole because they're further away, they're in the potential well of the galaxy. So those make narrow lines in the spectra. And then surrounding in the same kind of equatorial plane as the disk and broadline region, there's what we call a torus sometimes. It may or may not really be a solid. It may be like little clouds itself. It may be filaments. It may have a funny shape. But the idea is that there's lots of dust in this geometry, in the sense that if by chance the line of sight from the observer from our telescope to the AGN is through this torus, the dust will block the accretion disk and it will block the broadline region. So what happens in a spectrum is we don't see broad lines, but the accretion disk makes this very blue spectrum. So we also don't see that blue rise from the accretion disk. Whereas if we're looking by chance, it's oriented such that we have a view of the center within the torus, then we can see a very blue spectrum and we can see very broad lines. So these are two example spectra from DESI to really illustrate what I was just describing. So the top spectrum, so those are, I tried to shift them to align them in the rest frame. So this is this F lambda in rest frame in wavelength and angstrom. So you can see in this case that the top one is type 1, so very blue spectrum from the accretion disk, and then these broad lines come from the broadline region clouds, and the image also looks blue. It looks like a blue point source. And then the other object is a type 2 HGN. It does not look so blue, and the spectrum also is not so blue, but there's this very strong narrow emission line from the narrow line region here. So when we see broad lines and a blue spectrum, it's pretty easy to say, yes, this is an AGN, this is a quasar, no problem. However, when it's just narrow lines, it's not so easy because narrow lines could also come from ionized gas from young stars. So how do we tell apart narrow lines from stars and narrow lines from AGN? One of the most famous diagnostic is called the BPT diagnostic diagram. And it's the ratio of O3 over H beta line versus N2 over H alpha. And this is using SDSS. And then the distribution of points of galaxies show a branch of star-forming galaxies in red, and then this plume of AGN. So when you have an AGN, you go to both higher N2 over H alpha and higher O3 over H beta. So this traces the photoionization potential here, and then this traces the metallicity of the gas, the N2 over H alpha. And then these two lines, the solid line and the dashed line, are the typical demarcation used. So this is, the dashed line is maximum starburst line, guaranteed an AGN above this. And then in between, it's called composite. So it's basically these galaxies may have a mixture of AGN and star formation in them, and they may also have various other processes like shocks as well. So this diagram has been used very commonly, and here I'm going to advertise that at the Data Lab, we have a notebook that shows how to use the SDSS catalog, one of the catalogs with emission line measurements, plot the BPT, and then draw these squares, and in each square, draw 100 spectra and stack them to get very good signal and show the average shape. So from star forming, composite, and then liner and Seifert is how we also divide the AGN. You can see that the average spectra look pretty different. And namely, this is zooming in on the regions of these specific emission lines. And then if you zoom in further, we can see that the O3 over H beta ratio, for example, varies quite a lot. And then this is the N2 over H alpha at these two lines here in the spectrum. So this is used a lot still nowadays, very commonly. One issue is that with optical spectra, O3 and H beta, we can observe out to redshift 1, but N2 and H alpha, we lose them at redshift about 0.4, 0.5. So in order to be able to go to higher redshift, because we want to trace the evolution of AGN and black holes, there's been a number of efforts to make replacement or alternative diagnostic diagrams. So I'm showing one example. Well, I'm not showing it yet, but I will show you one example. And the usual approach is to say, okay, let's start with the regular BPT diagram, which I just introduced. And then its little cousin here, the Weyer-Osterbrock 87 diagram. So this is O3 over H beta versus S2 over H alpha. And then the points are color-coded here for the 4 categories I showed you before: star forming in blue, composite orange, and then Seifert or AGN in red, and then liners here in green. So once we code when we classify the galaxies according to their BPT class, we can say, well, can we replace N2 over H alpha with something else so we can use O3 over H beta out to higher redshift, out to redshift 1. And then there's been a number of examples. So for example, the color has been used or the stellar mass has been used. But in this case, in this work here by Zhang and Hao, they're using the width, the line width of the oxygen 3 line. And oxygen 3 is quite bright in the narrow line region, specifically of HGN. It's also can be bright at low metallicity in galaxies. So what happens if we replace N2 over H alpha with the width of O3, so sigma O3, we get a similar, less good, okay, there's a bit more scatter, but we still get some separation between star-forming galaxies in blue and basically everything else. And these authors propose this diagonal line to split between HGN and star-forming galaxies, and then they have a further split to examine composites. Okay, so maybe we could try using this diagram with DESI and see how far that takes us. So before doing that, one point to note is what happens with broadline HGN. So broadline HGN, well, we know they're HGN, so we don't really need this diagnostic, but where do they reside? And that will help us confirm that HGN are indeed up and above this diagonal line. So we can see that indeed they're mostly here, but if we look at them in 2 bins of redshift, and this is again from that paper by Zhang and Hao, they found that it's very easy for the higher Z, which also are higher luminosity HGN just because of the detection limit. It's very easy for luminous HGN, but fainter HGN that we find to low redshift can also cross on the other side. So one thing we're going to try to do is to slightly improve this diagnostic by taking into account the information that, well, for type 1, maybe we can use the broad lines as a line width in addition, as an additional piece of information, and not just use the width of the O3 line. So this is what we're going to do, but first let's start with the usual Keck diagram. So what I'm showing here is the bright galaxy survey only. So these are lower redshift galaxies, and they're bright galaxies. And these galaxies, they have a main survey, so they observe, well, the main survey already has a bright and a faint component, and those are a mixture of galaxies and HGN and quasars. But what happened with the bright galaxy survey is we had a star-galaxy separation that would remove stars to focus on galaxies, but that would also remove by accident some quasars. So we define also a BGS AGN type, so bright galaxy survey AGN, to put those quasars back in. So, and we just finished this paper. You'll find it on the archive next week. And this is basically proving, like, how do we prove and demonstrate that the BGS AGN are indeed quasars, and what's that sample like? Like, what can we learn from that sample compared to the rest of the bright galaxy survey? Okay, so if you look at the top, this is just the distribution of the line width of O3. So the BGS AGN sample in red is much more biased toward wider line widths, and we're expecting this because we're expecting AGN, so this is good. And then if we plot the Keck diagram, we can see that they are mostly, and so if you focus, all the colored points here are all the BGS AGN sample, and they're mostly all on the right, and in particular, the red dots are visually identified as quasars. So we checked all the spectra, so this is about 520 spectra. We checked them all one by one, and we have a by eye classification, so visual classification, which is what these color symbols are. So all the red dots are where they should be. But here we don't really distinguish between type 2, type 1, because we're measuring O3, and O3 is always a narrow line, even in quasars, except if there's an outflow. But still, it's not a broad line, like it's not from the broadline region. So the idea is to replace O3 with the maximum line width that we find in the spectrum. So for a given spectrum, if we look at all the lines, is there a broad H alpha or broad H beta or broad magnesium 2? And what's that line width? So that's what we use for, we call the sigma max on the horizontal axis. So what does that do? Well, this tells us visually very quickly the difference between type 2 HGN with narrow lines and type 1 with broad lines. Because type 1, this is log of sigma. So they have the Gaussian sigma, so it's another factor 2 for the full width F max, is already over 1,000 kilometers per second. So those are very broad lines. So what do we learn from this? So the histogram shows that, yes, the BGS sample has both AGN with narrow AGN and broad AGN, but the BGS AGN sample specifically, which I did not mention this, but this was chosen also with infrared colors. So it was chosen with independently from we did not know in advance what the optical spectrum would be like. This is really successfully picking up a lot of these more broad line, like quasar type spectra. And then the bottom is the Keck diagram, so the same line. So you can see that what we identify by I, so the green triangles here are narrow line AGN, and then so as different from quasars. But interestingly, we can start to learn even extra, because if you notice, there's a few points in between. So what's going on? Why this is not a perfectly clean bimodality separation? So it turns out that with such a large survey, we get a lot of these more rare AGN. And then they're not that rare, but comparatively, there's a subcategory they call narrow line Seifert 1, which is like a bit of a conflict, because it's like saying you have a narrow broad line. But if you do look at the spectra here, H alpha on the right side is broad enough that it's kind of blended with N2 doublet, but it's not a real broad line. So what's super interesting with these narrow line Seifert ones is people are now starting to find them at very high redshift with JWST. And one of the possible explanation is that it's a lower mass black hole, but it's accreting. It's basically a very young AGN that's accreting a lot. So it's like growing fast, but it's a low mass right now. So it's like one of the earliest growth phase. So it would make sense that JWST would find them at high redshift. So maybe those are low redshift analogs of earlier AGN that are growing fast. So these are just 3 examples from the small BGS AGN sample, but there's many more, obviously, in a DESI spectrum. Okay. So I've been, let's see how I'm doing with time. Okay, I think I should be wrapping up. I'll just show one other kind of more rare kind. So in the model I showed before, there was a black hole with accretion disk and torus, but sometimes there's also a radio jet. It's not always there, but when there's a radio jet, the radio jet itself can have different signatures in the radio wavelengths. But there's also, if by chance we're looking at an AGN, but we're looking right in the jet, this is what we call a blazar, basically. And the spectrum also in the optical will look different in this case, because we're looking, we have the light coming from also like a lot of non-thermal light, and we're not really looking at the broadline region or narrowline region like a regular, necessarily like a regular quasar. And then I just wanted to show, because we were not necessarily expecting this, but we're visually inspecting the spectra. And I was looking at these ones, I was like, those are very odd, because there's no emission lines, or very weak. There's some very weak emission lines, but barely. No broad lines. And there's some stellar absorption lines. But normally when you have just stellar absorption lines and you have a red spectrum, it's like an older galaxy, like a early type or elliptical. But this has this blue light. So like, are those blazars? So we took a peek in the radio data, and this is the VLA survey, sky survey. And then you can see that they have booming, obvious radio emission. So we're pretty confident that, so those are more rare in the sense that we have by chance to be looking directly into the jet, and the jet is very collimated. But it just shows the fact that having such a large survey like DESI, for example, we're bound to find such a wide diversity of AGN and quasars, and this will allow us to learn about many aspects of supermassive black holes, and ultimately how they also relate to galaxy evolution. So today I was basically mostly showing you like some small highlights and kind of early results of what we've been learning with DESI. There's much more to come. And then we've been working on using, but also improving and modifying AGN dynastic diagrams. And this is because we're currently creating a number of catalogs that we will release to the public, so everyone can use them to study AGN and quasars. We're already analyzing the data release 1, which is right now only internal, so it's not yet to the public. And this is 10 times bigger than the early data release. And then I didn't get to talk too much, but I want to mention that several of us are also applying machine learning techniques to the spectra, because one thing we can do, and I guess I do have one slide to advertise briefly from Goja Sudek. So one thing we can do is train a model, and in this case, this is using an autoencoder to use the entire spectrum. So instead of using emission lines, H beta, O3, H alpha, we can use the entire spectrum and then train the model on the spectrum. And then so the model will first reduce a dimension. So a spectrum, let's say we start with 1,000 elements, you can reduce to like 6 dimension or 10 dimension in a latent space. So this is showing basically a view of classifying according to AGN star forming or other, like using basically BPT type of diagnostic, but see where do they end up in this space. So this is projecting down to 2 dimension. So the axes don't mean much, but what we're trying to do here is to find if the model is separating the spectra as being different. And then, so using again a 2-dimensional space, you can find that the broadline HGN are separated quite well from the narrowline HGN and from the star-forming galaxies here. So this is working. This is just one example, but yeah, there's a lot of potential that if you want to ask questions, I'm happy to take questions, and I'll stop here.
Okay, so thank you very much, Stephanie. Very interesting and exciting work. We have time for question. Alberto, you can unmute your microphone and ask your question.
Yeah. So this was really a great talk, Stephanie. You really summarized the key point of the AGN problems right now. So I have a few questions. One of them is, do you guys have any time-dependent study of the data? Are you coming back to the same spots over some times, or?
Yeah, that's a very good question. So we are, but we only have very few epochs. So the spectra normally, to get the full depth of DESI, we need maybe between 2 and 4, sometimes maximum 8 passes. So for quasars, because they normally get this kind of number, like 2 to 5 maybe. So it's not very many observations, but sometimes those can be spread over just a few nights or over months. So we also don't have a specific cadence. So we don't have, for example, like I know SDSS has like a black hole mapper project, and they have a cadence and they revisit for reverberation mapping, for example. So we don't have that, but there's still an experiment being done trying to see, we don't have many epochs, but we have many quasars. So can we do a statistical analysis of how they vary with time? Even if each of them, maybe they only have 2 or 5 epochs, but we also have the photometry from other surveys with light curves. So maybe statistically, we can do an ensemble study. So it looks like it could be doable, but yeah, we don't have a specific time domain, part of the experiment.
Okay. And if I have time for another question, have you guys tried to classify the AGNs between radio loud, not radio loud?
Not yet. The exception is in the Red Quasars paper by Vicky Fawcett et al. So they specifically did there a cross-match with radio to examine radio properties. And we're just starting to look at cross-matching with FIRST, for example, from the radio, and then I guess it's VLA-SS, the last survey. But we haven't, one difficulty, as I guess you may already know, but in the radio sky looks very different from the optical sky. So finding the counterparts is not always easy. But I think this will be very interesting because DESI, especially now with the year 1 and year 3 data, we have such a big coverage that there's going to be a lot of interesting overlap. But we haven't done very much yet.
Okay. So I will stop here. If later nobody else want to ask something, I have one other question.
Yes, go ahead.
Okay, I was very interested in your results about the luminosity functions because you guys are finding a lot of AGNs at very high redshift. Actually, you mentioned redshift of 5 or so, and those are very interesting for the black hole mass growth, as you very nicely pointed out. I was wondering, have you guys produced already some luminosity function at those high redshift? And maybe compare with the theoretical predictions, or is
Let
that
me
something
see.
that is still going on?
Yeah, I mean, I think there will be more. I'm trying to remember just because it's been a while since that paper now, but I would suggest to look, sorry for the eyes. I'm gonna go back to the early slide on this. This one. Yeah. Oh, I don't have the full reference, but if you look at the paper by Yang
Okay.
et al., this will have, I'm trying to remember if it has a luminosity function in it.
Okay.
It may.
I can
So
check.
I would start there, but there will be definitely more papers from, so this is called a secondary program for DESI. So I'm pretty sure we will have that. We also are looking at we're making like X-ray luminosity function, for example, by cross-matching with X-rays, like from XMM, and eventually we can do with Rosita. So this will also be else to look for. So I think for HGN, it would be interesting to have optical luminosity function and X-ray luminosity function both. And myself, I like to also see O3 luminosity functions.
Okay, really nice stuff. Thank you.
Thanks.
Well, we have some time for questions. Well, I have one question, and I would like to ask you if you have any contaminants when you select quasars in your sample.
Yes. So I skipped some of those details, but I mentioned, for example, that DESI as a QSO target type specifically. So those are meant to be quasars, but they're not all quasars. So some of them end up being stars or galaxies. So we have a default pipeline that's called Red Rock. So this is run on all the spectra, and this will classify the spectra as QSO, galaxy, or star. But we also have what we call them afterburner pipelines. So one is called QuasarNet and the other one is called Magnesium-2. And QuasarNet is machine learning based, and it will search for broad lines and it will assign a probability of being a broad line. And we found that Red Rock does not find all the quasars. So QuasarNet helps to be more complete, and it finds another 5 to 10% maybe of quasars. And then the Magnesium-2 together and QuasarNet, I think, help. And so basically, if something ends up being classified a star, usually by the pipeline, it is indeed a star. So those are treated separately. So we can use the information. And then in the study I showed, the BGS AGN sample, so this was a smaller study in survey validation. So we did look at each spectrum visually also. So we had a visual class too. And this is to make sure how confident can we be then when we use later the pipeline and the Red Rock and QuasarNet and Magnesium-2? Is this going to be good enough? Are we still worried? And then in some special classes, like the red quasars, those are very difficult, even for the pipeline. So we end up doing visual inspection, or spots. You still have to look at some of them. So it turns out that people sometimes are still better than computers. But
yeah, well, it's very hard work to select visually all the objects.
Yes, we don't want to visually inspect everything. So that's also why we're exploring using machine learning for fine-tuning the classification of the spectra. So we can train with some smaller set that we visually classify and then have the model learn the classification.
Have you already tried machine learning techniques for the classification, or is it
yeah, so
progress?
just this one slide I showed. This is one example. Sorry, I'm gonna go back to the end. Yeah, I went fast. but this is using an autoencoder.
Ah, that
And it
one,
is-
okay.
Yeah,
Yes.
it's defining like two axes, which they don't have a strict physical meaning, but they learn from all the spectra. So this is one example. So QuasarNet, like I mentioned, is already machine learning. And I have a separate effort that we've been doing too. I guess if you can, start looking, at some of these papers here. These are all mostly based on autoencoders. And I think it's like one way that you can use the information of the entire spectrum.
Okay, thank you very much. So if there are no more questions, I think we can stop here. Thank you very much, Stephanie. I enjoy it a lot. Very interesting talk. And thank you very much, everyone, for joining us.
Right. Thanks, everyone. And feel free to get in touch if you ever want to follow up or if you have more questions.
Thank you. Thank you, Stephanie. Well, bye.
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 Bye, thanks.